After understanding the existence of electrons and holes, we next describe how they move around in a semiconductor. There are two driving forces for moving electrons and holes. They are diffusion and drift. If there are more particles at the particular locations, they will try to spread out to the less dense region. This process is called diffusion. Now, imagine that there are more electrons on one side of the band. These electrons will be driven to the other side by diffusion. Or with a different notion, you may also say that the empty spaces or holes are also diffusing from the right to the left like bubbles moving in water. We will further explain this later. Another way to move the electrons is by applying an electric force to tilt the band so that the electrons will be moved by the potential energy gradient. The electric force can be applied by adding a voltage source, for example, a battery. The negative terminal of the battery raises the energy of the electrons so that they are driven to the positive terminal following the potential gradient. The motion of carriers caused by an electric potential difference is called drift, and the electric force is proportional to the voltage difference applied. In reality, drift and diffusion can coexist, and it is more obvious from the fact that electrons carry charges. Assuming that electrons have non-uniform distributions and are concentrated at one end of the band. This also represents accumulation of negative charges, causing an increase in electron energy at that location. Electrons on the left are thus being pushed to the right by both diffusion and drift. Let's take a closer look at the conduction band under a small net force. There are a lot of spaces or holes and only very few electrons. The electrons tend to spread out evenly to avoid charge accumulation. When an electron is being pushed into the system from one side, it tends to redistribute the existing electrons and push the last one out. Normally, we consider electrons are moving and they are responsible for carrying the electric current. In the valence band, all the available spaces are filled with electrons. It is not possible to push any electron into the material from an external source. It is just like a car cannot enter a jammed road. In order to have the electron entering the material on the left, an electron needs to be removed on the right first. It is like moving a space or a hole into the material from the right. This hole allows another electron next to it to move to the right, which is equivalent to having the hole moved to the left. It is like how bubbles move in water, in which it is more natural to say the bubbles are moving rather than the water molecules are moving. Eventually, the electron on the left is allowed to move into the material when the hole moves out. Therefore, in the valence band, we usually consider the holes as the carriers for electricity. In general, you need both electrons and holes for electrons to move in the bands. And the motion of the one with smaller quantity is easier to observe. Therefore, electrons are considered to be the carriers in the conduction band and holes the carriers in the valence band. As we all know, an electric current is composed of moving charges. In metal, electrical conduction only takes place in the partially filled band when a voltage is applied. Therefore, either holes or electrons account. You do not count both of them. In a semiconductor, electric conduction takes place in both conduction band and valence band. They are distinct conduction paths, one like on a flyover and the other like underground tunnel that carriers cannot be mixed. Therefore, you have to count currents in both the conduction band and valence band and then sum them up to obtain the total current. The total number of carriers, however, is usually still much smaller than that in metal. That is why semiconductor is less conducting than metal.